you need to pause, read. Other than that, I'll just go ahead and get going. You're gonna pull some sort of mass to the right, a distance of 0.32 meters, and that is the amplitude. And the problem states that at 0.32, the box at rest, and it wants to find a couple of things here. It wants to find the time from 0.32 to 0.16, which is halfway, and then the other one is from 0.16 to 0, so the other half. All right. So other than that, let's go ahead and get going with the time. In order to find time for this particular problem, you have to set up this particular simple harmonic motion function. X of t is given as a cosine theta. Therefore, we can go ahead and expand theta because we're not given an angle in this one because it's not revolving on a circle. Here, you can translate theta into omega t. So by definition, omega is the change in theta over change in time. So if you were to solve for theta, theta would equal to the angular frequency here times time. All right. Other than that, we know what x of t is. In part A, it wants us to go from 0.32 to 0.16. So my x of t here is 0.16 because that's the position that I'm interested in. All right. Other than that, x of t is 0.16. What is your a? Your a is your amplitude. In this particular problem, it says that you're going to stretch the system 0.32 to the right and kind of hold it and then release it. So my amplitude is 0.32. And then here I broke up omega, angular frequency, into 2 pi over capital T because it didn't give me angular frequency or angular speed here. So I can just go ahead and break that up into 2 pi divided by capital T. Okay, T being the period of oscillation, which is actually given to me in this particular problem. The problem says, if you read it, it's a period of 0.9 seconds. So here I broke that up so I can utilize the information given to me. And then t to the right here, small t here, is any time, which is part of the function I just carried out. Okay. Other than that, in order to solve for t, I can just go ahead and do a little algebra here. I'm going to go ahead and substitute in t for 0.9 because that was given. And then the next move I want to do is I'm going to divide both sides by 0.32. So make sure you watch the algebra here. This is where people can goof with algebra skills. So the first algebraic step I need to do is divide both sides by 0.32. So that'll be 0.16 divided by 0.32 on the left side. And as you can see here, you have cosine in parentheses. So you have 2 pi, 0.9, and t. Okay. Well, the next move you have to do in order to get t by itself is to get rid of cosine. So this is very similar to the unit on projectile motion with the range function. So hopefully you've practiced then. Well, how do you get rid of cosine? Well, divide both sides by cosine. Therefore, on the left side, which I highlighted here, this is cosine to the -1 or inverse cosine. Okay, so anytime you divide both sides by cosine, when it goes to the other side, it has to be cosine inverse. And in parentheses here, I have 0.16 divided by 0.32, or you can simplify it down to 0.5 if you want, because 0.16 and 0.32 simplifies down to the 1/2, okay, which is 0.5. And then as you can see here on the right side, all I did was I just carry all my work down, 2 pi 0.9 times t. But I do want to point out that this is the other error folks can make. So you notice here in this function here, cosine is 2 pi, but the unit for 2 pi is 2 pi rad, okay? So sometimes folks will leave their mode and calculate their calculator mode in degree mode, which I highly encourage you to reassess. 2 pi is units of rad, so it's important that you make sure your calculator's in rad mode. Okay, so I made a note for you here, so hopefully you're watching this video carefully. It's important to check your mode as you do harmonics. You need it to be in rad mode because 2 pi is 2 pi radian. We just don't write out the unit rad. If you want, you can. It doesn't change anything. Okay, so if you do this particular step that I highlighted in blue, inverse cosine of 0.5 in rad mode will give you 1.0472. And then to get t by itself, I multiply both sides by the 0.9, so I brought it up. And then at the same time, I divide both sides by 2 pi. So if you do all this algebra stuff correctly on your calculator, you should get a time of about 0.15 seconds. Okay, so make sure your calculator is in rad mode, and hopefully you're using parentheses as you practice all this algebra manipulations. All right, so that is the answer for part A. So it takes about 0.15 seconds to go from 0.32, aka the amplitude, to about midway. Okay. Now, this is what I just found. This arrow that's just dropped down, I just found this t to be 0.15 seconds. Okay. I do want to point out that a common misconception that folks might often have is that they think the period is just a time to go halfway from amplitude to 0, which is not the case, okay? And they might just take that and divide it by 2 because they're thinking linearly, so they might just take the distance here because it's half, and they'll just take the time divided by 2, which is super whack physics, okay? So make sure you apply physics function and hopefully interpret information correctly. All right, let's go ahead and crack out part B. Part B wants us to find the time that it takes to go from now midway back to the equilibrium position, right? So I'm just gonna go ahead and apply physics again. X of t is equal to a cosine theta. I want to break up theta into omega t, angular frequency divided by t. And then, well, what's my x of t? Well, in this case, my final position, it would be at 0 because now I'm starting at 0.16, but I'm ending at 0. So x of t is your xf, okay? Other than that, the right side stays the same. As you can see, nothing's really changed. The amplitude hasn't changed. You know, omega is still 2 pi over capital T. Once again, I introduced capital T because the period is given for me in this particular problem. Now, same algebra skill. Let's get T by itself. To get T by itself, divide both sides by 0.32. So 0 divided by 0.32 is just 0. Now, I simply have cosine of 2 pi over 0.9 times T. Well, the next step I need to do is get rid of cosine. So therefore, I'm going to inverse cosine of 0. But don't forget, your calculator must be in radian mode because you're dealing with 2 pi rad here, okay? Other than that, if you do that correctly, cosine of 0, inverse cosine of 0 in radian mode will give you about 1.571. And then I'm going to go ahead and multiply both sides the same as I did before by the denominator on the right side. So I'm going to move it up, aka multiply it. At the same time, 2 pi is in the numerator on the right. I want to move that down, or you can say divide both sides by 2 pi. And if you do that correctly, you'll get a time of 0.225 seconds. Now, it's important that you can interpret the information that you find. Well, t here is equal to 0.225. That is just, okay, for the whole entire motion. Okay, why? Because you started from the amplitude and you went all the way to 0. So this function allows you to find the time where it is that you stop from where you started, the amplitude. So here, the time that I just found is this green arrow all the way. So that time is 0.225. But that's not the time that they want in part B, okay? The time that they want in part B is from 0.16 to 0. Well, I mean, at this point, hopefully if you're taking physics, you can just reason it out. If it takes 0.225 seconds to go from amplitude to 0, and it takes 0.15 seconds to go from amplitude to midway, well, you can just take the difference to find the time that it takes to go from 0.16 to 0, okay? So, in order to find this black arrow here, because that's what essentially part B is asking for, how much time did it take for it to cover the second half here of the distance that's shown in the diagram, okay? So I would just take the difference. I would simply state that, well, I can take the whole time, which is 0.225. So it would take 0.225 from amplitude to equilibrium, but it only took 0.15 seconds to go from amplitude to midway. So 0.225 minus 0.15 will give you 0.75 seconds. And at this time, again, I like to take this time out to point out to you that the time here is not symmetrical, okay? So don't just find the time from 0.32 to 0 and then divide it by 2. That's a big misconception because the acceleration for harmonics is not constant. So because acceleration changes, your velocity changes and it's not linear. So don't simply just find the time and chop it in half. That's a big no-no. Alright, so other than that, that is the answer for part B. However, I wouldn't do all this work here. I would just think like this. So hopefully you're keeping up with the common sense here. The problem states that the period is 0.9 seconds. Well, what does that mean? It means the time for one full cycle. For the mass to start there, go left, and come back to where it is. So watch my arrow. The arrow that just bounced down there, that's 0.25 of a cycle. That's 1/4 of a cycle. Well, how do I know it's 1/4? Because this has to go all the way to the left, and that's another quarter, and then it has to come back to here, and that's another quarter, and it has to come back to here, that's another quarter. So as you can see here, there are 4 arrows, so therefore each arrow represents 1/4 of the period. Because period, watch my cursor, by definition is the time to start where you are, go all the way to where you stop, change direction, come all the way back. Well, that's 1 period. But in this case, 1 period is composed of 4 of these black arrows. So I can literally just say t divided by 4 is the time to go from amplitude to equilibrium. So I can find the time here from 0.32 to 0 really super fast. Okay, I'll take the period and divide it by 4. That'll give me 0.225 seconds, which is consistent with what I found. But once again, that's not the question. But once I found the time from 0.32 to 0, I can just use quick deduction and still take the difference to find the time from 0.16 to 0. Okay, if you need to listen to all that again, please do. Other than that, I hope that helps. Stay nerdy, don't be whack.